Hello everybody, welcome to part 6, more finding the zeros. We are going to do 4 examples. The first 2 will be cubic and the second 2 will be quartic. This is more of the same from part 5. Okay, our first polynomial will be probably the simplest one, a cubic. Here is our beautiful cubic polynomial. A cubic polynomial does have to have at least one real zero. According to the fundamental theorem of algebra, it does have 3 total roots or 3 total zeros. However, since imaginary roots can only occur in pairs, there can be 2 imaginary roots, but then the third one still has to be real. So we do have to have at least, we're guaranteed at least one answer. The first thing that we're going to do is use the rational zeros theorem. I'll call this step 1 like I did before. We'll use the rational zeros theorem to find the possible rational roots or zeros. So we want to take all the factors of this constant here, which we can just think of as 6, and then all the factors of 3, and that's our mini p and mini q, or lowercase if you will. So our lowercase p is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, all the factors of the constant 6. Then mini q, factors of 3 are plus or minus 1 and plus or minus 3. All right, when q is not 1, we have to go another step and list all the possible rational roots by putting all the different combinations of p's over q's to find them. So you just want to make sure that you move methodically as not to miss anything. All right, my method is going to be to take each p and put it over each q. So I'm going to have 1 over 1, that's 1, so plus or minus 1, and then 1 over 3, which is plus or minus 1/3. Then I'm going to move on to the 2 and do the same thing. 2 over 1 is 2, and then 2 over 3 is 2/3. Then move on to the 3. 3 over 1 is 3, and then 3 over 3 is 1, and we already have a 1, so we don't need to relist it. Then we move on to the 6. 6 over 1 is 6, and then 6 over 3 is 2, and we already have that. So we have 1, 2, 3, 4, 5, 6 times 2 because they're both plus or minuses. So we have 12 possible rational roots. Now realize this only gives us the possible rational roots. So if one of the roots is rational, it will be one of those, 12 values there. The second one that we want, the second step that we want to take is to use Descartes' rule of signs in order to kind of narrow down potentially what we want to test. Descartes' rule of signs might lead us to finding that, hey, there might not be, a good chance of finding a positive root. Why don't you check the negatives, or vice versa? So that's why we want to use Descartes' rule of signs next. Now, Descartes' rule of signs tells us to count the sign changes in f of x, and that's what capital P is. Let's see if we have sign changes in f of x. Positive to negative, that's 1. Negative to positive, that's 2. Positive to negative, that's 3. So our capital P is 3. That means we can have the number of positive real roots can be 3, or we could go down by 2. 3 or 1. So we can have either 3 or 1 positive real roots. The next thing that we want to do is find f of negative x, and that's going to allow us to find the potential number of negative real roots. Finding f of negative x will give us negative 3x cubed minus 14x squared minus 17x minus 6. Then we count the number of sign changes in f of negative x. All terms are negative, so n, capital N, the number of sign changes in f of negative x is 0. That means the number of negative real roots is 0. We do not have any. Therefore, that means we don't have to test any of these negative numbers here, since they can't possibly be a root of our function. The next step is actually testing out some values here, and we're going to use synthetic division. If you think about why we use synthetic division, it's because it gives us a remainder very quickly. When we use synthetic division and get a remainder of 0, that means the number that we're testing worked. It is a 0 or is a root of that polynomial. So step 3 is to test values using synthetic division. And Descartes' rule of signs helped us determine which values to test. Since we can't possibly have any negative real roots, we're not going to test any of the negative values. So instead, I'm just going to move through and test the simpler positive values to test. I'm going to start with 1. So we'll put 1 in the corner. And then we're not skipping any terms here. We're going down from x to the third, to the second, to the first, and then our constant. So we don't have to put any 0 placeholders in. And then I'm just going to work through synthetic division really without explaining it. It's kind of fun to move through this quickly. Oh my goodness. Did that just work? Okay, that's pretty cool because I wrote this and I didn't remember what the actual answers were, but that one just worked, and it so rarely happens on the first time, so that was really cool. All right, so that means one of our zeros, roots, is x equals 1. That is really cool. All right, now because we started with a cubic, once we've performed synthetic division once, it's knocked us down by 1 degree. We now have this quotient here that remains is a quadratic. So this quadratic that remains is 3x squared minus 11x plus 6. With a quadratic, in order to solve it, we need to set it equal to 0. Now, please note that this equal to 0 has nothing to do with this remainder of 0 here. This remainder of 0 is only telling us that the number 1 is a 0 or a root of our f of x. We are now left with a quadratic, and a quadratic will provide the final 2 roots of our cubic. Now, we can deal with a quadratic in a couple ways. We can factor it if it's factorable, or we can use the quadratic formula. Now, this is technically factorable, but we have not gotten into factoring into kind of this complex. So I'm just going to use the quadratic formula to show that it always works, even when it's factorable or not. So our a, b, and c are as follows. And then the quadratic formula, if you recall, is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That is our quadratic formula. If you don't have that memorized or written down somewhere where you can easily access it, please do. Okay, so we are going to use our quadratic formula. So the opposite of negative 11 is 11, plus or minus, then we square 11, minus 4 times a times c, all over 2 times a. From here, I want to see what our discriminant is. 4 times 3 times 6. 4 times 3 times 6 is 72, and then 121 minus 72 is 49. So we end up having 11 plus or minus the square root of 49 all over 6. Now 49 is a positive number. That means that we will have real roots to this. The discriminant's positive. 49 is also a perfect square, meaning we're going to have rational roots. So this is 11 plus or minus 7 all over 6. 11 plus 7 is 18. So one of our other answers is 3. 11 minus 7 is 4. And 4 over 6 is 2/3. Now note, these are rational solutions. Were they a part of the rational zeros theorem? Was 2/3 in here? Yes, it was. Was 3 in there? Yes, it was. What if we didn't first check the number 1 and instead first checked 3? And it worked. Well, we would have had a different quadratic. And if we got 3 as our answer here, then we would have gotten 2/3 and 1 from the quadratic. The moral of the story is that this cubic has a total of 3 roots, and we just found out that they're all real. They actually also happen to be all rational. What am I doing? There's a star. X equals 2/3. So here's our 3 real and, more specifically, rational, and of course they're all positive. Let's look back at Descartes, our boy Descartes. Of course, he told us there's no negative real roots. None. There could be either 3 or 1 positive real roots. Dun dun dun, he was right. Okay, here's our graph. Pretty exciting. We can easily see that we cross at 1, and then we can see that we cross again at 3. It's harder to see 2/3, but if I clicked that point, and you can see it's 0.66, 7. 0.6 repeating technically is 2/3. But there's our first root, our first 0. It has a multiplicity of 1. It occurs once. Here's our root of 1. It has a multiplicity of 1. It occurs only one time. And then our final one is over here when x is 3. So pretty exciting. We found those 3. I guess it just depends on your definition of exciting, but I think that's pretty cool. So there's our cubic polynomial in all its glory. In example number 2, we want to do the exact same thing. So again, we have a cubic. We're going to have 3 roots. At least one of them could be real, or all 3 of them could be real. So we want to find those real zeros or real roots. The first thing we're again going to do is start with the rational zeros theorem. And this lists all of our possible rational roots for this cubic. So we're going to list the factors of 1, which are plus or minus 1, and then those are p-values, and then the factors of 2, those are going to be our q-values, so plus or minus 1 and plus or minus 2. Remember, this theorem is also known as like the p over q theorem, and therefore we list all of the p's over the q's. So just thinking about this is 1 over 1, which is 1, and 1 over 2, which is 1/2. So our possible rational zeros are plus or minus 1 and plus or minus 1/2. Second thing we're going to do is try to narrow down, even though there's only 4 potential rational zeros for this polynomial, Descartes' rule of signs may be able to narrow it down even more for what we should test out. So Descartes' rule of signs will tell us how many positive real roots we can have and how many negative real roots. To find how many positive real roots, we need to count the sign changes in f of x. Positive to negative, that's 1. Negative to positive, that's 2. That's not 1. So p is the number of sign changes in f of x, capital P, it's 2. So that means we can have either 2 or 0 positive real roots. So we can go down by multiples of 2. The next thing that we want to do is find f of negative x. And f of negative x will be negative 2x cubed minus 9x squared minus 2x plus 1. The way I can find that quickly is whenever there's an odd exponent, like here 3 and here 1, that means that plugging in a negative x changes the sign of that term. So both of these terms went from positive to negative. When we have an even exponent term, the term doesn't change at all because plugging in a negative and then raising it to an even power doesn't change anything. So this negative 9x squared stayed as is. The constant is unchanged because it has nothing to do with the x. Okay, now we want to count the number of sign changes here. Only 1, negative to positive right here. So n, the number of sign changes in f of negative x is 1, and that means we have 1 negative real root. We can't go down by a multiple of 2 because then we would be less than 0, and that doesn't make sense. All right, so we know we have to have 1 negative real root. That means I'm going to test the negative numbers first when I do the synthetic division. The first value that I'm going to test is negative 1. So negative 1 goes in the corner. We're not skipping any terms in our function, or polynomial rather. All right, this one's not going to work because we didn't get 0 as a remainder, so negative 1 doesn't work. Then I'm going to test negative 1/2 next. Yeah, it can be kind of a pain sometimes to test the fractions, but it shouldn't be too bad. 2 times a half, well, 2 times a negative half is -1. I always like to think about saying, if you're multiplying a half by something, saying half of, because of means multiply. So this is a -10. So half of 10, right, is 5. And they're both negative, so it does happen to be +5. And then we have a 7. Negative half of 7 is, I'm just going to use decimals here, -3.5. Whoops. And then whatever this happens to be, in this case, it's not 0. All right, so neither one of our negative values worked. Okay, well, it is possible that, you know, we could have positive real roots. So let's test those. All right, I'm going to test +1. And again, we'll do synthetic division. Remember, our goal is to get a 0 remainder, since that means that x value would end up being a root or a 0. We'll get -5. Goodness, this is not working. Okay, 1 doesn't work either. I'm going to try one more time. If 1/2 doesn't work, then I did something wrong, at least for the types of problems that I would be giving you guys. So 1/2 should work. Let's do 2, -9, 2, and 1. Bring the 2 down. Half of 2 is 1. Half of -8 is -4. Half of -2 is -1. All right, this one works. All right, that means that our first answer, our first root that we found is 1/2. And I've been writing the solutions up the top there. So 1/2 works, that's great. Okay, because we started with a cubic and we divided successfully, that means that we're left with the quadratic. So this quadratic here is part of step 4. Solve the quadratic. I don't know if I have given this step a name yet, but solving a quadratic usually means use the quadratic formula unless it's factorable. So this is 2x squared minus 8x minus 2, and we set it equal to 0 in order to solve it. I do need to make a little bit more room here, so I'll move this off to the side. And it looks like I can factor out a 2 from this quadratic and just make life easier. And that's totally legal. All right, this is not factorable because there's not 2 numbers that multiply to -1 that add to -4. So we need to use the quadratic formula. Don't worry about the 2. It doesn't matter. A would be 1, B is -4, and C is -1 for the quadratic formula. Okay, quadratic formula, opposite of b, plus or minus the square root of b squared. Always positive, by the way. Minus 4 times a times c, all over 2 times a. Okay, our discriminant, let's see what the value is under the root. 16 plus 4, so our discriminant's 20. Our discriminant happens to be a positive number, and recall from the previous chapter, when your discriminant's positive, that means you have 2 real roots. 20 is not a perfect square, so they're not going to be rational, but they will be real. They'll just have a root in them. So we do need to break down the square root of 20. We can break down the square root of 20 into root 4, root 5, and it's still all over 2. I'm going to keep moving this so we can keep working on it. The square root of 5, or sorry, the square root of 4 is 2. So we have 4 plus or minus 2 root 5 all over 2. Then we can triangle simplify the 4, the 2, and the 2. The 4 becomes a 2, the 2 becomes a 1, this 2 becomes a 1. So we have 2 plus or minus 1 root 5, which we don't need to write the 1 in front of the root 5, nor do we need to write over 1. These are our final 2 answers. One of them is 2 plus root 5, and one of them is 2 minus root 5. So our 3 final answers, I will write over here in white. X equals 1/2 is one of them. X equals 2 plus root 5, and x equals 2 minus root 5. Those are our 3 answers, our 3 roots to this cubic. Now, what did Descartes say from the very beginning? Descartes said that we will either have 2 positive real roots or none, and we'll definitely have 1 negative real root. Let's see if that's the case. Did we have 2 positive real roots? Yes. 1/2 is positive, so is 2 plus root 5. The 1 negative real root is here. 2 minus root 5 is a negative number. Now, these two numbers are not rational. They're real though. This is a rational number. Let's go back to the rational zeros theorem. This gives us the possible rational zeros, meaning if we had any rational zeros, they would be one of these 4 numbers. And it was. 1/2 was a root. However, not all of our roots end up being rational, and that's why we need to use things like the quadratic formula to find them. Here is the graph of our cubic, and here are the 3 roots written in blue to the left. 1/2, let's take a look at that one first. That's the easiest one. There it is, multiplicity 1. And then let's take a look at the 2 minus root 5. Root 5 is like just a little bit bigger than 2, right? Because root 5 is a little bit bigger than square root 4. So when we do 2 minus root 5, my Alexa told me that it was negative 0.23. So I don't have my calculator by me right now. So here it is. There's our negative real root. Again, not a rational number, but a real number. We can see it here. And this goes on forever, but I just approximated it with the squiggles. All right, 2 plus root 5, what's that? That is 4.23. Travel all the way over here. Boom. There is the 2 plus root 5. So all 3 of these cubics roots ended up being real. One of them is rational, and the other 2 are just real. This next example is our first quartic polynomial degree 4. This one is, we follow the same process, but it's a little bit more complex because when we do the synthetic division, dividing it once only knocks it down to a cubic. So we then have to divide again. So we need 2 successful synthetic divisions in order to knock it down to a quadratic. Let's begin by once again doing our first step, which is using the rational zeros theorem. So our little p is 3, and so the factors of 3 are plus or minus 1 and plus or minus 3. Our q value, lowercase q, is just 1. The lead coefficient is 1, so it's just plus or minus 1. Therefore, the possible rational zeros are only plus or minus 1 and plus or minus 3. The next step is to do Descartes' rule of signs to kind of help us gauge if those real roots are going to be positive or negative. The number of sign changes in f of x is 1, just 1. So p, capital P is 1. Therefore, there is 1 positive real root. So that's helpful, 1 positive real root. Then we need to find f of negative x to determine how many negative real roots we'll have. So we'll again have x to the 4th, that term doesn't change, minus 2x cubed, that'll change, minus 2x squared, that term doesn't change, plus 6x, and then minus 3. So let's see how many sign changes we have here. We have 1, 2, 3. So our capital N value, the number of sign changes in f of negative x is 3. Therefore, we can have 3 or 1 negative real root or roots. So that helps us a little bit, but we do still need to check both positive and negative values. Step 3 is to test values using synthetic division. I'm going to start by just testing out positive 1. Again, I'm testing these values here, the potential rational zeros. So I'm going to start by testing positive 1 using synthetic division. You can see that synthetic division is a much better process, I think, than the polynomial long division, which would take far longer if we had to keep doing that over and over. All right, our remainder is not 0. Not going to work. Let's check the other positive value of 3 next. So when we check this one, we can see if 3 ends up being a root. Looks like we're kind of getting way far off here. 33 times 3, oh my, that's 99, and 99 minus 3 is 96, so we're kind of off. But the cool thing is that what we just found is, if you recall the remainder theorem tells us what the actual value is the remainder. So like f of 1, and this is just a little bit extra here, but f of 1 is -8, and then f of 3 is 96. So that's pretty cool. That means in between, using the intermediate value theorem, since we had to slice through the x-axis here to get from -8 to 96, we had to literally go from all the way from -8 all the way up to 96. We hit a 0 in between when x is 1 and x is 3. Now we don't have any values to test in between those, so that's going to probably come from our quadratic formula, but that's pretty cool. All right, I'm going to check -1 next and see if that works. Checking -1 is the same process, again, doing the synthetic division. This can get a little tedious, but synthetic division is nice because you can move through it fairly quickly. But it is easy to make an error on this, so you just do have to be careful. Awesome, it looks like -1 is one of our solutions. It's one of our roots. So x equals -1. Great. So it looks like that was one of our negative roots. Now here's the thing, we cannot just move on to step 4 yet. The reason being is something I said at the start of this example. We now have only gone from a quartic to a cubic. What we have here is a cubic polynomial. It's 1x cubed plus 1x squared minus 3x minus 3. We obviously can't do the quadratic formula on a cubic. It's too big. So we have to keep using synthetic division in order to find out what one of our other roots is. So we have to keep using synthetic division until we get down to a quadratic. And since we started with a degree 4, we have to do synthetic division successfully 2 times now to get it down to the quadratic. So we do know that -1 works. We also know that 1 and 3 don't work. So what I'm going to do is sort of scratch out the +1 and the +3 there. I didn't mean to actually scratch out the 1. Just the +1 and the +3 don't work. However, -1 works, and we could also test -3. So it's up to you. You could test -1 again. Remember that just because a number is a root doesn't mean that you can never test it again. This root might have a multiplicity of 2 or 3. We don't know. So this root might occur more than once. I'm going to test it again using this for synthetic division now. So now we're going to keep using synthetic division on the cubic function, which is down here. So I'm again testing, the only numbers I really can still test are -1 and -3. I'm just going to test -1 and see if it works again. It could work more than once. So I have a 1, a 1, a -3, and a -3. That is what I'm now dividing into, the cubic. So I bring down the 1, 0 times -1 is 0, -3 times -1 is 3, awesome. That ended up working again. So that means our root of -1 has a multiplicity of 2. It occurs twice because it worked again. Now, if you had tested -3, you would have found that it actually did not work. You could have done that, but we needed to get down to a quadratic. And again, we had to successfully do synthetic division 2 times because this time we started with a quartic. Now we have a quadratic function. Now we can move on to step 4. Note that the quadratic that we have does not have a linear term. There was a 0 here. So it's x squared plus 0x, which you don't need to write, minus 3 equals 0. You do not even have to do the quadratic formula on this one, although if you did, it would still work out pretty nice. Here's a really quick way to solve this quadratic because it does not have the x term. If you add 3 to both sides, you end up just getting this, and then you take the square root, and then we have plus or minus root 3. If you do the quadratic formula on this, if you do, a would be 1, b would be 0, and c is negative 3. If you do that, you should still get just plus or minus root 3 at the end. I'm not going to go through the whole quadratic formula for this one because this was an easy quadratic to use without the quadratic formula. So step 4, again, is to solve the quadratic. Okay, so we have our 4 roots. Here they are. We found x equals negative 1, and that has a multiplicity of 2, so that counts for 2 of the roots. Then we have positive root 3, and then we have negative root 3. Let's find those on the graph. Here is our graph. Descartes said that we would have one positive real root, and we do. It's root 3, approximately 1.73. And then he said we would have either 1 or 3 negative real roots. Here's 2 of them, and here's the third. So we can take a look more onto our graph and see our positive real root is root 3, 1.73. Then our negative real roots are over here. We have negative 1, and it has a multiplicity of 2. Since it bounces back. And then this is negative root 3, or negative 1.73, and it has a multiplicity of 1. This last one I'm not going to go through. It will be a you try problem, but I will provide just the answers, not the worked out solutions. If you're interested in finding the worked out solutions, you can join me at my office hours today if you do have questions on that, or just ask me, and I'll gladly, show it to you. But go ahead and get this written down. This is a great one. Go ahead and go through all the processes that we've done. Rational zeros theorem, Descartes' rule of signs, test using synthetic division. Remember, since this is a quartic, you need 2 successful synthetic divisions, and you can still check the same value if it works once, because sometimes roots have a multiplicity of 2. You should have 4 answers at the end. I will reveal the answers in 1 second, so if you don't want them yet, go ahead and pause your screen and you can end the video now. Here are your solutions. Thank you for bearing with me through this extra long video, but I hope those extra examples really did help.